We want to prove Cauchy's integral formula, and I'm going to lead into it with a simpler case to start with. So we have a circle centered at A, and so I want to show that if the closed contour gamma is a circle centered at A with radius r traversed once in the counterclockwise direction, the integral of 1 over z minus a over the circle is 2 pi I. And 2 pi I is a big deal in complex math. You see it over and over. And so we're gonna take this thing and parameterize it. So I'm starting here with it, but we're gonna parameterize and make substitutions. So if you think about this, this is just z, where it now if we held the radius constant and only theta is moving, this would be a circle at the origin, and this makes it a circle centered at A. So we're making z dependent on theta, and so this is going to be our z, so this turns into this. And then we replace dz by thinking dz d theta would be I r to the e I theta. And then d theta can come over here instead of here, and we replace dz with this. And so here that is, and this is where it's been substituted in. And now the a's cancel, these things cancel, and just leave I, and I is not dependent on theta, so it can come out front, and this is this, which is 2 pi, and there we go. So we're seeing that this integral is equal to 2 pi I, and that's our result. So now let's move on to Cauchy's integral, and we're going to use Cauchy's theorem as the basis. And I'm not proving that here, but I'll put a link to my proof of that in the description. But Cauchy's theorem has a situation where if you have two closed contours, so this could be just miscellaneous shape. It doesn't have to be, this one is not meant to be a circle. This one we are going to make a circle. But Cauchy's theorem says that the integral over gamma 1 is equal to the integral over gamma 2, whether or not there's a singularity in the middle, but we're making a singularity here. Now this would be equal to this, but now to reflect that singularity, because Cauchy's the great use of Cauchy's integral formula is when you have a singularity contained in the contour that you're trying to take the integral of. And so if this is equal to this, then this is equal to this. We can introduce a singularity at A. So now on the basis of this, which is just this, it's just the same thing. And what I'm going to do is I'm going to leave the integral of gamma 1 alone, and we're going to work on the integral of gamma 2, which is a circle. We're making it a circle. And so now we're basically there because I've already shown all the parameterization. So from here, we get to here. Remember, we're leaving this alone, and we're taking this and working on it. So from this, we parameterize, we get to here. And from here, we get to here. And now the last thing we're going to do is, again, on the basis of Cauchy's theorem, we can deform these contours as big or as small as we want. And so we're going to take this circle and take the limit as r, the radius, goes to 0, and we're going to deform it all the way down to the point A. And so that gets us from here to here. Okay, that's the main move that we have to do here. And now f of a is not dependent on theta, so it can come out front. And so we have this, which is equal to this, which is equal to 2 pi. And so we get our result. And so we have shown that this is equal to this, and that is Cauchy's integral formula. So here it is. And then it's very common to divide both sides by 2 pi I. So we get this form of it. And now there is the generalized Cauchy integral, which all that is if you just keep taking the derivative of both sides and follow the pattern that emerges, then you get Cauchy's generalized integral formula. But I'm not going to do that here. I'll leave that to you if you want. And that is Cauchy's integral formula.